Thank you very much. Let me just get my screen sorted. So my name is Tunde. I'm a teaching associate at the University of Strathclyde, and I am going to be talking about our PIERSdynamic model, which is one of the outputs of my PhD, and how it can be used to predict adverse maternal outcomes. So what our research focused on is what happens after the diagnosis of preeclampsia. So there is a small proportion of women who are at the highest risk of outcome as soon as or just after they had their diagnosis. And so they need to deliver as soon as possible to start the recovery process and try to avoid some adverse outcomes. But the question remains of what about the rest? So the majority of women remains under expectant management for days to weeks, especially if they were diagnosed early preterm. So timing of birth is especially important for them. And the use of predictive models is already recommended to assess maternal risk. And there are models that already exist, such as the rest of the models in the PIERS family. However, the existing models are all either meant to be used on admission, so they are mainly used for identifying this small proportion at the highest risk, or they can be used at any point in time, but they don't really account for what happened between admission and the time that we are using the model. And this can actually be a problem, as in many things that we measure to predict the maternal outcome, the same values can mean different things depending on if it was measured on admission or after the patient has been monitored for a week or two. So even those not so extreme values can become alarming if the numbers have been creeping up over time. So this is exactly why we need a model that doesn't just use a snapshot of time to make predictions, but instead uses all of the available information from the individual woman's clinical course since her diagnosis with preeclampsia. So that we can make predictions not just based on the current values, but also on how the condition has been progressing since the diagnosis. So in this study, we attempted to do exactly that. We collected data from previously published studies and combined it to create a large data set of over 9,000 women. And they were from a range of low, middle, and high income countries. We used the data up to 14 days after first assessment because we expected about 75% of the patients to deliver with or without complications within 2 weeks after admission, just based on the protocols in place during the studies. And we also added some additional variables describing the health systems where the data came from so that we can account for any underlying differences in the baseline risk from environment or the healthcare of the country. The outcome that we modeled was a composite maternal outcome consisting of maternal mortality and a range of life-altering morbidities. And we took the first occurrence of any elements of the composite outcome, and that was recorded for each patient. And we modeled this first occurrence within a 2-day rolling window to allow some time for decision on timing and place of birth. So this was a very large data set and also a follow-up for a short period of time. So there were missing values in the data, and these were handled using multiple imputation. And then 75% of the data was used for model development, where we fitted a model using binary mixed effects random forest with tenfold cross-validation. And then the final model was tested on the 25% of the data that was still remaining. And this was not used during the model development, and it was imputed independently. So it was a good, robust internal validation of the model. The performance was assessed using area under the ROC curve, area under the precision recall curve, and also classification into 5 risk groups from very low to very high. So first, the area under the ROC curve. Actually, by 14 days after the admission, approximately 80% of the women have given birth without complications, and a further approximately 10% of women experienced at least one component of the outcome. So by the end of the 14 days, only 9% of patients still remained in the dataset. And in fact, just under 80% of women were removed from the dataset by 7 days after admission because they were either discharged after delivery or experienced an outcome. So the amount of data that we had decreased very rapidly a couple days after admission. So the area under the ROC curve, it was estimated to be above 50% on every single day that we looked at, and 50% would be the equivalent of just randomly assigning patients to outcome and no outcome categories. It was also above 70%, which would class as good discrimination for every day for the first week and also on a couple days after. Beyond the first 7 days, the area under the ROC curve was still near 70%, but the confidence intervals were very wide because the number of patients just dropped to so little comparatively. We also had a look at comparing this PIERSdynamic model with the repeated use of the PIERS-ML model. So PIERS-ML is a static model that's meant to be used on the day of admission only. But based on the current recommendation, we expect that maybe people might use it repeatedly to try to keep track of how the risk changes, which it wasn't intended to be used for, but we wanted to assess to see what happens if it is used this way. And as we expected, the static model performed really, really well on day of admission, but then starts getting worse and the performance and also quite unstable pretty much the day after admission, while the dynamic model is quite stable for the first 7 weeks. And even afterwards, it doesn't get nearly as unstable as repeating the static model. So this was the area under the ROC curve. This measure is actually not very good a measure to use when we are looking at data that has very low rates of outcomes, because the correctly identified no outcomes are going to outweigh any of the rest of the measurements that are used to calculate the area under the ROC curve. So we could actually get a pretty good value by just saying that nobody has an outcome. A better measure to use is area under the precision recall curve, or AUPRC. So that's what we had a look at next. So AUPRC is better than AUROC when the data is unbalanced because it ignores that large chunk of the correct negatives, but it is a bit more difficult to interpret than the area under the ROC curve. So the area under the ROC curve, a random classifier would be around 50%, but for the area under the precision recall curve, a random classifier would be near the fraction of positives, which is just the outcome rate in the data. So the bigger the difference is between the fraction of positives and the AUPRC, the better the model performance is. And we are seeing a similar performance. So performing really, really well for the first 7 days and starting to become a bit more unstable for the rest of the 14 days when we had a very small amount of data left. But what's interesting is even then, there's only just a couple days near day 10 where it is actually very close to the fraction of positives. And the rest of the time it's looking like it's doing better. So this is still indicating a really good performance over time. And it is also possible that we're seeing this big drop, not because the model is performing worse, but because we're getting rid of people. So it could be possible that if we had the same amount of people over time, we could have a more stable and better performance even beyond the first 7 days. And again, comparing this to the repeated use of the static model, the static model performs really, really well on day of admission as it's meant to, and then starts dropping in performance very quickly. And after about 2 days after admission, it is actually not different from just randomly assigning people into outcome or no outcome groups, while the dynamic model stays performing very well for 7 days and is also performing better than a random classifier for the rest of the 14 days. Now, finally, we also use the predicted probabilities. Sorry about that. So we also use the predicted probabilities and some predetermined risk thresholds to categorize patients into 5 risk groups on each day. So what you're seeing here is a Sankey diagram of the change in classification on the first 7 days. So for each day, the bars show the proportion of patients classified in the respective groups, and the bands between the days show the movement of patients between groups from one day to the next. So throughout the first week, the model was doing really well in ruling in the outcome. From one day to the next, the patients in the very high and high risk groups are only moving to experience an outcome or remain in their own group. The high-risk patients are also moving down to moderate risk on most of the days, but they don't go any lower than moderate risk from within the space of one day. Patients in the very low risk group were mainly remaining in very low risk group or delivering with no complications. But they also moved from very low risk to low and on a few occasions even to moderate. So that's a bit higher jump than what we would like to see between the groups. And low risk had the most movement over time. They moved both higher and lower from one day to the next. Most of them delivered with no complications, but there was also a small portion who experienced an outcome the day after being classified as low risk. And both the low risk and the very very low risk groups were doing better over time. It's not shown here, but they were actually performing quite well beyond the first week. So it's kind of indicating that the model is really good at identifying high risk straight away, but they need longer observation period to confidently identify those who are at the lowest risk. So overall, the model already showed clinical utility by identifying women at the greatest risk of adverse outcome for the first 7 days after admission. And we could also identify women at lowest risk after sufficient data collection period. So both of these could be used to allow the model to support decision-making. There is also still future work to do for this study. First, the model should be externally validated in diverse datasets, which is something that we are actually currently working on. And if possible, data should be collected beyond 7 days after admission, so we could test if the model is still performing well once there is sufficient data to test it in, or if we need to perhaps use a different model to predict beyond the first 7 days. But overall, this is what we have discovered with the dynamic model. It is performing quite well and much better than what we've seen from the repeated use of static model, which is currently recommended. So hopefully the use of dynamic models is going to be more useful for longer term monitoring of patients. Thank you.
Okay, thank you very much. And it's lovely to see that work being done, because we always wondered what's going to happen as the next stage after PIERS, the initial predictive model of PIERS. So that's a really very interesting work, and we look forward to see the future work that you're doing.